All right, so sometimes when we're solving these, we're going to get extraneous solutions, which means they don't make any sense at all. Now, as we've seen before, some solutions do not satisfy the original equation algebraically, and that's what's going to happen is it's not going to make sense. And so for logarithms, remember, the log of x will always be positive. So we always have to make that positive, and so that's going to be the key. Well, when we're looking at this equation, what do we see? Well, we see kind of a mess. We have e to the 2x equals e to the x plus 2. What if I suggest we take everything to the left side? Well, what does that do in helping us? Well, now let's look at our values. Here, if we think about this, whenever we have things, if we had an x squared plus x plus, 2, well, we have a power of 2, we have a power of 1, and here we have a power of 0. Okay, well, that's kind of what we have here. We have a 2, we have a 1, and e to the 0 is 1. And so that's kind of the same form we have, except instead of using x's, we're using e to the x. So kind of a little different trick here. And so what we can do then is, can we factor this? Well, how are we going to factor it? First off, that's going to be the key. Well, we're going to use e to the x, and we're going to use e to the x as our first term, because that times that is going to give me e to the 2x. Now, what factors of 2 are there? Well, there's 1 and 2, and I have a negative, so I have to have one positive and one negative. But the key is the larger has to be negative. So the larger has to be negative, the smaller has to be positive. Now let's distribute again. That's e to the 2x. Then we have minus 2ex plus e to the x. So that's going to be minus e to the x minus 2. Aha, so we've got the factored form now. So this is something you have to think about, factoring weird things like this. Now we set each of these equal to 0. So e to the x plus 1 equals 0, and e to the x minus 2 equals 0. Okay, and so now we're going to subtract 1, subtract 1. E to the x equals a negative 1. We've isolated it so we can take the ln of both sides. And here we have the first issue, ln of negative 1. Before we said that that doesn't work. And so that doesn't, this whole side, this one doesn't work. So that is not going to be a solution piece. Well, what about this one? Well, here we're going to add 2 to both sides. It's looking better already. E to the x equals 2. Now we can take ln of e to the x equals ln of 2. Bring down our x ln of e equals ln of 2. Well, that's just 1. So x is equal to ln of 2. And that would be our solution. So this would be extraneous because it's not going to work. So that one, we throw it out. It's going to give us some weird things because it can't take the ln of a negative. But this one, it does work. And so that's going to be our solution. All right, so now we're going to use the definition of a logarithm to solve logarithmic equations. So for any logarithmic expression, for any algebraic expression S and a real number b and c where b is greater than 0 but not equal to 1, then log base b of s is equal to c. If you remember, b to the c equals s, and that's what we have here. And so that's kind of how we're going to think about this. We're going to have to go the other way or this way. We're going to go back and forth using this notation. So we need to get and solve for ln of x. So to do that, we're going to subtract 6. So ln of x equals 10 minus 6 is 4. All right. Now, how are we going to solve this? Well, remember, this is log base e to the x is equal to 4. So now we can say e to the 4 is equal to x. So we're going to convert whenever we have ln to log base e, so then we can take e to the 4 equals x using this notation. Okay, and so what does that mean? Well, that's going to be our answer, and we're going to assume they want it in the most exact answer form possible, which is e to the 4. We could plug that into our calculator and get a number. But that's not going to be as exact as just leaving it as e to the 4. All right, what about this one? Well, we're going to do basically the same thing as we did here. We're going to isolate the ln. So if we isolate the ln of x plus 1 in this case, we're going to divide both sides by 2. So that gives us ln x plus 1 equals 5. Now what do we do? Well, now we're going to take and say, well, this is log base e of x plus 1 equals 5. And then we're going to take e to the 5 equals x plus 1. Well, we just want x, so if we subtract 1 from both sides, we get x is equal to e to the 5th minus 1. And again, that is going to be our exact answer. We don't have to go any further. That's all we need to do. Okay. All right, sometimes we're going to use a graphing calculator to solve these too. And so in this case, it says use a graphing calculator to estimate the solution of the logarithmic expression 2 to the x equals 1,000 to 2 decimal places. Well, how do we do that? Well, if we remember, we go and we plug in 2 to the, to the x on that one. We plug in 1,000 on that one. We graph it, but if we know we have to have that min and max closer to where the 1,000 is. So I'm going to say let's go from 999 to 1,001, and we'll go by, I don't know, 0.1. That doesn't matter. And so all we care about is that intersection point. So intersect number 5. So blue one is the first curve, looks good. Red one's the second curve, looks good. Our guess, I'm just going to guess right there. And it tells me the intersection is x equals 9.9657. It only wanted it to 2 decimal places, so 9.97. And that would be my answer. So x is approximately, I should say, 9.97. And then that would be my solution to that using the calculator. Now, could I solve it otherwise? Yeah, you could still solve it, taking the ln of both sides and divide and get all that stuff. But we want to show you that the calculator is another way to do it, because we could have done it the same way as we did there. We could have taken the ln of 2 to the x equals the ln of 1,000. Bring that down. X ln of 2 equals ln of 1,000. Divide by ln of 2. And so x equals, and this will give you the same value as that. Okay, or at least it should. So maybe we should check. So if we go back here and we do that, we do ln of 1,000 divided by ln of 2, we get 9.97. So it works. Again, 2 different ways to do this, same answer. All right, what about this one? So here, what we want to do is we want to solve ln of x squared is equal to 1, ln 1. And so what do we need to do? Well, remember, if we have, say, e to the x and equals 1, we can take the ln of both sides, and then that gives us x, and then that goes to ln of e equals ln of 1, and so we can do that, and that becomes 1, so x is equal to ln of 1. But we can also take, when we have this way, we can go back the other way. And how do we do that? Well, we're going to take e to both sides. And if we take e to the ln of x squared, and that's equal to e to the ln of 1, that's going to give me, well, when I take e to this, that's going to give me x squared. And when I take e to that, that's going to give me 1. Well, now I have a quadratic, basically. I can look at this 2 ways. I can say, okay, well, that's x squared minus 1 equals 0. So I got x plus 1, x minus 1 equals 0. So x is equal to a negative 1, and x equals plus 1. And that would be my 2 solutions. Or I could have said from here, I could have taken the square root of both sides. And so x equals plus or minus 1, because when you take the square root of 1, it's still 1, but you have that plus or minus, and here's our plus and minus. And so both of them give us the same answers. But we had to remember that when we have ln's, if we take e to that, then the x squared is going to be what's left, and here what's inside here is left, and so we have x squared is equal to 1. Now again, we can always, if we forget our formulas or anything else, okay, well, let's say we had ln of, instead of x squared, let's say we had ln of 4. Well, what we said was e to the ln of 4 is what? What's 4? So instead of x squared, we just put our 4 here, which would have been 2 squared. But that is equal to that. And that's kind of another way to show, if you forget, you can use your calculator to kind of remember some things by testing to make sure, am I doing this right? Because that's always a possibility. You think you know it, but you don't want to use it because you're just a little bit uncertain. And using your calculator, you can show that, when you do this, you just get what's inside of here, whether it's the 1 or the x squared. All right, so the next one says, how long will it take before 20% of a 1,000 gram sample of uranium-235 has decayed? All right, well, what do we need? Well, it looks like they give us this nice little amount of stuff here for this formula, gives us some half-lives, and so we're doing uranium-235, so we're doing this bottom row here. So that's like half-life is 703,800,000 years. So quite a long time. And so that's one of the reasons why storage of all the waste is kind of an issue here. So that's because we have such long half-lives. All right. So this is the equation we're going to be using, where A naught is the amount initially present. Well, how much is initially present? Well, it says 1,000-gram sample. So let's say, well, that's 1,000 grams. And then it says times 1/2, so that's a normal number because we went half-life. Then little t is the time period over which a substance is studied. Okay, well, that's kind of what we're looking for. So we're going to look for that one. And big T is a half-life of this substance. Well, we found that over here, so that's in the table. And so AT is going to be how much is going to be left over at the end. Well, we want 20% of the sample to be decayed. So how much is left over? Well, left over is only 800 grams. Okay, so we have to think about that in the proper way. This is left over, and we said 20% is decaying, so 20% is going to be gone. What's left after that? Well, that's 80%, which is 80% of 100, which is going to be 800 grams. So let's write that equation now as we have all the numbers plugged in. So we have 800 equals 1,000 times 1/2 2. Now we don't know the little t. That's what we're looking for. And we know that that's 703,800 and 000. Now we want to solve for t. Well, what do we need to do? Well, we need to isolate this something to a power. And if we do that, we'll divide that by 1,000. And we'll divide that by 1,000. So that says, we have 0.8. And that is represented as 80%. So we have 80% of a sample left, is what basically it's saying, is equal to, now I'm going to leave some space here because I know what I have to do. And so then we have 703,800,000. Okay. Now, how do we solve something like this before? Remember, what if we had, 2 equals 3 to the x or something like that? Well, we took the ln of both sides. And so that's what we're going to do here too. We're going to take the ln of that, and we're going to take the ln of that. How does that help me? That helps me by being able to bring that down in front. So then I have the ln of 0.8 equals, then we have t over 703,800,000 times the ln of 1/2. Now I need to solve for t. How do I solve for t? Well, I need to get rid of this ln of 1/2, and I need to get rid of this 703,800, and all that. So I'm going to multiply by the reciprocal. So I'm going to multiply by 703,800,000 over ln of 1/2. Okay, because that will cancel that. That will cancel that. And I'm multiplying the whole thing times it. So I have to remember to multiply this piece times that. So when I do that, that gives me t is equal to, now I have the ln of 0.8 times, and now I have 703,800,000 over ln of 1/2. Okay. Now guess what I get to do? I get to plug all that into my calculator. So let's clear that. And so what we said we had was the ln of 0.8 times the 703,800,000 divided by ln 0.5. And hopefully that gives us the answer. And so again, it's another long amount of time. And so that's how long it's going to take for 20% of the sample to decay. So let's write that down. We'll put in some commas so we kind of know what that is. So that was 226572993.2, and this was years. And so if we go and put that, that's 226,572,993.2 years. So quite a while for 20% of the sample to decay. 50% of it's going to decay in 703 million years or 704 million years roughly, but 20% of it will decay in that amount of time. All right, so that's all I have. So hopefully that will help you with this section.